So welcome everyone. This is the last IvS seminar of the academic year, and today we are going to learn about exoplanets. So it's my immense pleasure to welcome Dr. Dan Bauer. He's a research staff at ETS Zurich, and I know him for a few years now already, and I'll need to So Dan did his bachelor's in the UK in geophysics already. So he was already specializing towards geophysics, and then master's in fluid flow in industry and the environment. So that was in Cambridge. And then he moved over across the Atlantic and moved over to Caltech for his PhD in planetary geophysics. And afterwards, he continued there as a staff scientist. And then he moved back to Europe in 2015 at ETH as a research fellow, and then to University of Bern as an Ambizione fellow. And then he continued there at the Center for Space and Habitability. And only recently, earlier this year, he moved to ETH Zurich. So Dan is going to tell us about magma oceans and the earliest atmospheric evolution of rocky planets. And the floor is yours, Dan.
Great. So, thank you, Kaustubh, for the introduction. And indeed, today I'm going to talk about rocky planets in general, rocky exoplanets, but also rocky planets in terms of ones in our own solar system. And so this is going to be a big sort of picture talk about how we can best understand how these planets evolve from their earliest formation and evolution through to their present-day state. So, as Kaustubh just mentioned, I've had a sort of a winding journey through various physics departments, astronomy departments, planetary science departments, earth science departments, and in order to sort of capture that, I just generated my ADS word cloud here, so you can go on NASA ADS and do this when you have some papers, publications, and abstracts. And the reason that I'm going to show this is because I started out my career as a geodynamicist, so interested in looking at how the interior of Earth evolves over millions of years, hundreds of millions of years. And so, my earliest work was really working on Earth's mantle and, of course, generating models, fluid flow for that. But you can see now, as I've moved towards the field of exoplanets and planetary science in general, there are now other words that are cropping up in my word cloud. So ocean, this is actually magma oceans, not water oceans, but also atmosphere and surface. And I think this is interesting because what it's now demonstrating is that to understand holistically rocky planets and how they evolve from their earliest stage through to their mature state requires an understanding and appreciation of these major planetary reservoirs. Okay, so increasingly it's difficult to treat one reservoir in isolation from the other reservoir when you're thinking about planet evolution. And I would say, although we've had this idea for solar system planets to try and integrate the coupling of reservoirs, I think exoplanetary science is really pushing us now with new observations that I'll show to try and get a much deeper connection between the atmosphere, the surface, and the mantle, as we try and understand the overall processes that are governing the evolution of rocky planets. So a little bit about the group that I'm at. So the group is the exoplanetology group. So that's actually experimental planetology, and this is led by Professor Dr. Sosi. And we are based in the geochemistry department, geochemistry and petrology. And the essence of, or the key work that we're involved in is actually using experimental geoscience techniques to try and provide new constraints that we can use to understand rocky planets. So this here is a gas mixing furnace. So this is quite a simple operation. Basically, this little box gets really hot, up to about 1600 degrees C. And then you can pump in a variety of different gases, and you can then look at the equilibration between gas phases and melt compositions. And then you can cool the whole sample, and you can analyze your quench samples afterwards, and it will tell you something about the interaction of the melts and the gases. This here is showing a novel setup that we have at ETH. This is an aerodynamic laser levitation furnace, which should make everybody excited just by the name of it. But essentially what happens is a small bead, a little piece of rock basically, is put in this gas stream here, and it's actually levitated. Okay, so it's like this little spinning glass bead. Okay, you point a laser and you melt this glass bead. Okay, and then what happens is you can analyze the emission spectra or the transmission spectra, or indeed quench the sample and look at how the composition has changed as a consequence of evaporation. Okay. So the nice thing about this, of course, is that it allows us to do experiments in the time frame of a few minutes, okay? Whereas usually in geoscience, particularly at high pressures, you're often taking weeks in order to sort of set up your experiments, equilibrate them, or maybe even months. So in short, the group is providing new and novel lab constraints to understand the formation and evolution of rocky planets. And importantly, we're also trying to synergize the experimental side with also new modeling capabilities. So for motivation, I would just like to start with something that is hopefully familiar to everybody, which are the three planets, so Earth, Venus, and Mars. And we're just going to look at their present atmospheres. And rather than thinking about the abundance of one particular species, we're just going to normalize by the amount of nitrogen that are in the atmospheres. And it should stand out to you that even though Mars and Venus have very different total pressures, surface pressures at present day, if you actually look at the CO2 over N2 ratio, you can see that they're relatively comparable, okay? Whereas if you look at Earth, you can see that this is 5 orders of magnitude less, okay? So that should immediately sort of give you, a question or raise a question as to why is Earth different, okay, to Venus and Mars, and how does this relate potentially to how Earth has evolved subsequently to become a habitable planet, whereas at least at present day, Venus and Mars are not. So this is one of the motivators we have from the Earth science and planetary science perspective. But of course now, we're also in the age of JWST, and what this is allowing us to do is really probe the atmospheres of more distant planets. So these could be large gas giants, of course, but in the case of what I will talk about today, I'm going to focus mostly on the smaller bodies. So these are more like sort of sub-Neptune size and super-Earth. So again, the observations of planetary atmospheres is very much like any observations you make from the astrophysical side, where you essentially have a light source, which of course is your star, and this emits a continuous spectrum. And then here on this schematic, there's a cloud of gas, but of course in the context of what I'm talking about, this is the planetary atmosphere, and this cloud of gas is heated, and if it is hot enough, you will then be able to look at the emission spectra. Okay, so this will give you a brightness versus wavelength. You can also look at how much of the energy is actually passed through the cloud of gas, and in this regard, you end up with an absorption spectrum, or equivalently a transmission spectrum. Obviously, the two are very simply related. So emission and transmission are the two main ways in which we're now probing the exoplanetary atmospheres with JWST, and of course have always done so. It's just that JWST is providing such fine resolution and an extended wavelength range. So this isn't just something that will happen, this is now happening, and this is an example of a exoplanet K2-18b. Okay, so for those that are familiar, the exoplanets have all these interesting area codes associated with them. This one in particular is one of the first that has been characterized spectroscopically. And just to give you a feel, this planet is about 9 times as big as Earth. It orbits a cool dwarf within the habitable zone. It's about 110 light years away from Earth. And the reason that this has been so interesting in this community is because now we are able to make detections of these different species in the atmosphere. The question is, what type of planet is this? And remember, for exoplanets, the two main identifiers we previously got from observations are the mass and the radius, okay? But now we're able to supplement those data with spectroscopic information. And even though this is, a good fit in terms of determining the amount and the detections of these different species, it still has raised questions about what is the nature of this planet, okay? So for example, for this planet, there are 3 hypotheses, okay, all been proposed within essentially a year. So one is this notion that it's a Hycean world. So Hycean was coined by this work by Madhu, And the idea here is that you have a large hydrogen envelope, and what it does, it has PT conditions, so pressure, temperature at the base of the envelope that can sustain liquid water, okay? And so you get hydrogen and ocean, and that makes Hycean, okay? However, another model that can explain the data is to actually have a magma ocean world, okay? And the reason for this is that if you have liquid water or magma, okay, some of the gas species can dissolve into those liquid reservoirs, okay, and I'll talk about this more. This is based on solubility. And depending whether you are a Hycean world or a magma ocean world, and depending on the thermodynamics, you can actually explain, in particular, the lack of a nitrogen signal here, of an ammonia signal. There's other models that have been proposed that this planet could, in fact, be a gas-rich sub-Neptune, and this is appealing more towards photochemistry, modifying the abundances that you see at the top of this atmosphere. Okay, there's a similar planet now, TOI 270d, similar in terms of expected equilibrium temperature. And again, you can see this, this nice spectra, relatively speaking. Again, remember, this is for exoplanets. You can see we have a strong absorption of methane, we have a detection of water, and also CO2 absorption, okay? So remember that prior, again, to this kind of information, we had some information about H2O detections for certain planets from Hubble, but of course, we didn't have anything like this resolution until today. Okay, another planet that you may have heard about, 55 Cancri E. So this is everyone's favorite lava world. So this is just an artist's impression here. It has an 18-hour orbital period, so it's very close to the star. And if it's tidally locked, which we're not completely sure about, but if it is, the day side temperature is around 2800 Kelvin, okay, and the night side is 1400 Kelvin. So this kind of planet sustains a permanent magma ocean on its day side, okay? And it's actually an incredibly bright star, so it makes it very difficult to capture the spectrum using JWST. But at the same time, this has been recently attempted, and this is a nice plot of the spectra here. And what I want to point out simply is that if you assume that this planet was purely evaporating rock, okay, then you would end up with a prediction like the red line here. So this is the emission spectra if the planet had purely a rock vapor atmosphere. But with the data, so this is from JWST, you can see that in fact the data generally matches a model better if the planet has a volatile atmosphere. So again, we're talking about H2O, CO, CO2, CH4, okay? So, and this is, again, now introducing volatiles as a main aspect of planet formation evolution that we need to understand, because this planet in particular might have been one that we would not have expected to have volatiles, okay? And yet the data is now showing us that particularly for carbon dioxide and carbon monoxide, actually volatiles could be playing a major role in terms of the signals that we are seeing. Okay, so also in exoplanetary science, again, the main observables we can get are the mass of the planet and the radius of the planet, okay? And so what people do is they generate these so-called mass radius diagrams, and there's this region of mass radius space which cannot be easily explained by having an Earth-like structure. So if you have a mostly silicate mantle and an iron core, these planets are generally too small to explain some of the radii of certain planets, and you can see 55 Cancri E sits here. Okay, so what has now been proposed is that some of these planets are actually a little bit inflated, okay, so they have a relatively large radius for their mass, and this is because the planets have a mixed rock vapor volatile atmosphere. So again, it's not just about evaporating refractory elements and having a vapor, it's very much now this idea that, in fact, maybe we have H2O, CO2 in the atmosphere, and this is sort of causing a sort of a radius inflation effect. Of course, not to the extent that you see with H2 atmospheres, but nevertheless, it's an effect that could explain this blue region here of the mass radius diagram. Okay, another fundamental observation from exoplanetary science has been essentially looking at the demographics of exoplanets. And a feature that you may have heard about is the so-called radius valley. Okay, so here what we're doing is we're just looking at an exoplanet catalog, and we're counting the number of planets per star, and we're plotting this against the planet size in Earth radii. And you can see that there is a valley here. This also has been known as a gap, but it's not strictly a gap because you can see the likelihood doesn't drop to 0. So it's now been named more correctly the valley. But either way, what it's demonstrating is that we have a deficit of planets with a radii of around 1.8 Earth radii. And the question is, why is that? Okay? So this feature is known as the radius valley. We also find that beyond about 2.4 Earth radii, there is a large drop-off in the number of planets that we detect, okay? And this feature has been known as the radius cliff, okay? And the reason that I'm introducing, again, these observational constraints is because volatiles have again been used to sort of explain these two features in the exoplanet population. So first of all, if we think about the radius valley, so this again is this region where we have the deficit of planets, okay? There are a few models out there, but one of the common models is to assume that for the larger planets, you have a hydrogen and helium atmosphere, and this gives you sort of a puffier planet. But on the other side of the radius valley, you're more prone to atmospheric stripping, and this then removes the atmosphere from your planet, or most of the atmosphere, such that you're left with a silicate and iron planet. Okay, so this is sort of one view. As people have then thought in more detail about how volatiles behave, we now have this model where we have H2O included. And what happens, of course, is as you move closer, migrate inwards towards the star, then you can begin to create steam atmospheres, large steam atmospheres. And this, again, gives you a relatively more inflated planet. But, of course, eventually when you pass too close to the star, again, you strip away all of your atmosphere and you're back to a silicate and iron core. There are other models that are, again, also based on looking at how atmospheres escape. And this one is showing how, so the radius valley runs through here. And this model is showing that actually just the other side of the radius valley, you may end up with pure helium atmospheres. And again, this is due to the differential escape rates of different species depending on their molecular masses. So volatiles, again, have a seemingly important role to play to explain observations. Okay, a final motivating slide is if we go back to this radius cliff feature. So remember, this is the drop-off in the abundance of planets for Earth radii greater than 2.5 or so. This feature also has not yet been thoroughly explained. But one model that fits the data is the idea that once you push to larger and larger planet size, what happens is you have a strong feedback between the planetary mass and how much of the atmosphere you can pull into the interior, okay? And this, again, is a dissolution effect. And this is because you basically have an enhanced solubility effect. And so what is actually happening here is that you have a H2, maybe helium atmosphere, but as your planet becomes bigger, more of that atmosphere is getting drawn into the interior, okay? And it's a sort of a non-linear effect, which causes then the planet fraction to fall off like this cliff feature shows. Okay, so all of those sort of introductory slides were really to demonstrate to you that today I'm going to tell you a story about volatiles, okay? Volatiles meaning species such as CO2, CO, CH4, etc. Okay, importantly, so these are the element names, so these so-called CHNOPS elements make up all the life on Earth, okay? So this is 95% plus of life is made of these elements. But importantly, we're now discovering volatile-rich atmospheres on exoplanets, okay? And so therefore, the temptation, of course, is to try and use volatiles to trace the story of planet formation and evolution, not just for terrestrial, nominally, potentially habitable planets, but also to try and understand other planets, such as sub-Neptune worlds. Okay, so where do magma oceans enter this story? Okay, so if we wind the clock back to a model for planet formation, we have the protoplanetary disk that forms around the star. There are then various processes that form planetesimals. potentially including pebble accretion, but the idea is eventually we have a planetary embryo, and once we grow to about Mars size, then the planet has enough mass to begin ingassing, potentially, the nebular atmosphere. So it can potentially take some of this surrounding gas and incorporate it into the interior, okay? Because of thermodynamics and equilibrium between the gas phase and the melt. Particularly for large planets, super-Earths, so when you're several times Earth size, you can draw in potentially a large amount of the surrounding gas into your mantle. So this forms then a so-called nebular atmosphere, and this is also occurring at the same time as you're differentiating your iron and your silicates inside the planet. Eventually, the nebular gas will dissipate, and then what happens is you've sort of turned the switch the other way, and now the volatiles that were in the interior could begin to degas, okay? And this will occur initially relatively quickly because you have an atmosphere and a magma ocean. So the magma ocean is this red region here. And so these reservoirs have a similar dynamic timescale, and they're able to equilibrate fast. And eventually, though, your magma oceans will cool, and you will end up with a terrestrial planet, which will have a solid mantle, okay, and it will potentially continue to convect and remove heat, but of course at a much slower rate. And now you have whatever your residual degassed atmosphere is, and this will be modified over longer timescales by geological processes. So you have, for example, volcanism on Earth, you have plate tectonics and silicon-carbon cycling, which is cycling over a much longer timescale, millions of years, of volatiles from the atmosphere back into the interior. So you can already see that based on this sort of picture of planet formation, volatiles are integral to how everything here evolves towards a terrestrial planet. So if we think a little bit about secondary atmospheres, so by a secondary atmosphere, I'm meaning an atmosphere that is outgassed from the interior, then you have a rocky planet with a magma ocean, okay? So magma oceans will mean that your planet is around 1400 K or higher in terms of the surface temperature, and you have your atmosphere. And the type of atmosphere that you will have in equilibrium will depend, of course, on what materials you've used to build your planet, but it will also depend on how soluble the major species are. So how readily will CO2 or CH4 dissolve into your magma. Okay, so here is our picture of our rocky planet. We have a magma reservoir, and we have an atmosphere, and we have some partitioning of species between the magma and between the atmosphere. So a simple way of encapsulating this equilibrium between these two reservoirs is in terms of a solubility law. And here we have a quantity x, which is the mole fraction or mass fraction, depending how you choose to express, that is dissolved in the melt. Okay, so this is the amount of, for example, CO2 that is dissolved in the magma. It is related to the partial pressure in the atmosphere of the species. And then there are two constants. One is a solubility constant, and one is a stoichiometric coefficient. So the coefficient here is essentially taking account of the governing reaction that is controlling the solubility. Okay? You've probably seen this expressed in sort of physics 101 as Henry's law, okay? So a very simple form is if there is a linear relation between the amount that you dissolve and the pressure, okay? In which case you just have this constant here. But in general, it's often generalized to have this stoichiometric coefficient as well. Okay, and importantly, when you are thinking about trying to model these multi-species atmospheres, the values of alpha and beta depend on the type of species, okay? So it depends on if you are CO or if you are CO2, and it also depends on what is the composition of the melt, okay? So what is how much magnesium, silicon, iron do you have in your melt will also control how species dissolve, okay? So now you can hopefully begin to get a feel for why this is an interesting problem, because different species will have different dissolution strengths. And different species will dissolve more readily than others, and this can then affect the chemistry of the atmosphere. So ultimately, the game here is to look at the major elements that are involved in these TROPS elements, and we can then express the major stable gas species. Okay, there are many listed here. Of course, when we're just trying to explain the observations, we particularly focus on the dominant carbon and hydrogen species. And ultimately, the speciation of your atmosphere, of course, depends upon the pressure, temperature, composition of your system. Okay, so everything is collapsing to sort of a classical thermochemistry analysis of the system. So what we want to do is to solve for chemical equilibrium given the total abundances and temperature. Okay, and remember the difference here compared to, say, a more simple gas network is we have to also account for the fact that some of our species are dissolving into a melt phase as well. Okay, so they're not just all readily available in the gas phase. Okay, a little bit about this concept called oxygen fugacity. So oxygen is a major element, okay, and therefore it has a strong controlling influence on the ratios of reduced to oxidized species. Okay, so at a given temperature, it sets the ratio of CO over CO2 or H2 over H2O. And you can see this just by considering this reaction here, this gas reaction. And the point is that this term here involving oxygen, it relates to the FO2. This is the oxygen fugacity. And so you can see that if you express the equilibrium constant, the FO2 is controlling the ratio of CO2 to CO and H2O to H2. So if we just plot this on a graph, we have the FO2 here. This is expressed in terms of relative units, but it doesn't really matter. Just think of this as being this term here. And you can see that as you nominally increase the oxygen fugacity, the amount of CO you have relative to CO2 decreases. Okay, so this sort of conceptually hopefully makes some sense. Okay, if you have a higher partial pressure of oxygen or a higher oxygen fugacity, then you're going to favor the oxidized species. You're going to favor generating H2O or CO2 rather than H2 and CO. And this, of course, also makes this parameter an interesting sort of target for exoplanet observations, because if we can, for example, detect and constrain relative abundances of CO to CO2 or H2 to H2O, then we learn something about the oxygen fugacity, which can be very helpful for understanding planet formation and evolution processes. Okay, so I would now like to talk a little bit about steam atmospheres. So potentially, even if you're not in the field of planets, maybe you've heard things about steam atmospheres. Okay, so it's been a very popular paradigm for several decades now in order to explain the earliest evolution of planetary atmospheres. But the question I would like to pose at this point is, how common are steam atmospheres? So if we wind the clock back and look at what was the origin of steam atmospheres for planetary science, you can actually track the original work back to some papers by Lang and Ahrens in the early 1980s. And this was sort of revised then by Lindy Elkins-Tanton in a series of papers from 2008 onwards. But in the original work, which was actually experimental work, what they basically did is they took relatively oxidized materials such as serpentine, which is sort of an evolved composition that today you find on Earth that is relatively water-rich. And essentially you just blow it apart in a lab, okay? And then what you do is you look at what the gas species are from that. And people, of course, because you start out with relatively oxidized, you find that you can generate a large amount of H2O and CO2 when you vaporize these types of rocks. Okay. Of course, from the planetary science side, carbonaceous chondrites, relatively early solar system materials, are also have a large amount of hydrogen oxygen that will also generate a large amount of water species. H2O, for example, when you vaporize it. So this was the original background in terms of the species that people were interested in and the types of rock. And then what Abi and Matsui did is said, okay, if we have these these sort of samples or similar materials that are entering and vaporizing in planetary atmospheres, this will generate a large amount of H2O and CO2. Okay? And so when you do the calculation, the mass balance, what you find is that you get around 100 or 1,000 bar steam atmospheres for the early Earth, okay, which is a lot, obviously. So obviously Earth today has 1 bar atmosphere, and that's not all water. These are orders of magnitude, and of course it's a very sort of extreme environment to have for an initial state for a planet. The challenge is that the early work did not consider the fact that when you generate H2O, that some of it will want to dissolve into the magma ocean. Okay, so it won't just all stay in the atmosphere where it's been vaporized. It will equilibrate with the magma ocean. Okay, and so it's actually been known for a long time, since 1964, that water has a high solubility in magma. Okay, so if you have a steam atmosphere, a large amount of that steam atmosphere will actually want to dissolve into your magma. It won't stay in the atmosphere. Okay, and so this is some of the earliest work that demonstrated this effect. And now in the lab, we're also looking at the solubility of water in more primitive compositions. So as I mentioned before, when people thought about this problem, they were thinking about relatively evolved Earth compositions. Whereas for early planet formation, we need to think about the earliest types of compositions of planetary mantles. And that's now what we've been doing with so-called periodic liquids. And basically, we're finding the same thing. We're finding that if you have a lot of water in the system, it will want to go into the magma, okay? So then when we set up models, what we are trying to do is begin with a molten planet, okay? So here we have the iron core is here, and the idea is that we start with a fully molten mantle, okay? So all of this gray area is initially molten, and then what happens is as the planet cools, which is ultimately controlled by radiative transfer in the atmosphere, the mantle begins to solidify, okay, and it begins to form crystals. And as you begin to form crystals, these crystals in the simplest model will sink to the base, and you will effectively crystallize from the bottom upwards, okay? And this, of course, is an interesting problem to then look at how does CO2 and H2O in the mantle outgas as this crystallization process continues. So this is work that I've been involved in a few years ago, built again on some previous work. But what we found in particular in this study is that the amount of CO2, the partial pressure of CO2, decreases even though you begin to outgas, even though you continue to outgas CO2. And I'll explain what that means. So here, what we're doing is starting essentially with a fully molten planet. Think about Earth, we just melt all of the mantle, we have a magma ocean, okay? And then what we're allowing the model to do is cool as a consequence of radiative transfer in the atmosphere, which itself is determined by the volatiles, okay? So as your planet cools from molten to a solid state, because CO2 is generally not very soluble, this governs the initial rate at which you can cool the planet, okay? And this is why you can see the red line, which is CO2. You have sort of a 70-bar atmosphere. But eventually, as your planet cools, you will have a relatively small amount of melt left, around 30–25%. And what happens then is that the water that was in that melt eventually has to outgas, okay? And what happens is it begins flushing into the atmosphere. And as it begins to flush water into the atmosphere, it dilutes the atmosphere. So previously it had CO2, now it has H2O. And so what happens is this dilution effect is so strong that it actually drives down the partial pressure of CO2, okay? So this is something that we pointed out in this 2019 paper because previous work had not expressed the mass balance correctly, and therefore they were finding that the partial pressure would always increase as a consequence of outgassing, which intuitively might make sense to you, okay? But the key point to remember is that partial pressure is relative. It's relative to the total pressure, okay? And this dilution effect is strong. So even though CO2 continues to outgas, the actual end partial pressure is less than what you started with, and that's because you flushed a lot of water into the atmosphere. However, what we also showed in later work is that even though water will enter the atmosphere actually, if you look at the diversity and the uncertainty in the parameters that we have, CO is actually the dominant species for most of the atmospheres that we consider. So if we, in particular, set this FO2 to be a value that we think is more appropriate for the early Earth, then you can see this whole red region here. This is basically the volume mixing ratio. So basically, in the atmosphere, the more red you see, the more dominant you are by CO. Okay, and so you can actually see that carbon monoxide is the most dominant species. And it's only once you drop below about 30% melt as you continued cooling that you can begin to outgas some water. Okay? Even if you can outgas the water, your atmosphere only becomes about 50% by volume mixing ratio of water. So this is hardly the large steam atmospheres, for example, that we've been thinking about previously. There's also a range of different reasons as to why you might imagine that you can't actually outgas the water. Okay? So obviously, if you don't have a large amount of hydrogen in the system, this will restrict your ability to outgas water. Carbon will also mitigate the outgassing. And furthermore, the ability to outgas once you drop below 30% melt fraction is also dictated by what is happening at the surface. Okay, so all of these models assume that you have, a continuous equilibrium between your gas and your melt. Okay, but eventually, when your melt cools, you will form a crust or a solid lid, and this will then prevent further communication with the atmosphere. There are a lot of other reasons to believe why planets may retain water, okay, during both the magma ocean phase and during subsequent evolution. Okay, so there's a hypothesis about the basal magma ocean. The idea here is that your magma or your magma ocean crystallizes from the middle out, and in this regard, you can maybe trap a lot of volatiles in this melt layer at the base. As your magma ocean cools, there's this process by which you're dynamically trapping melt as this cooling front moves through the mantle. And then there are various combinations of sort of these models that have been put together. So in short, there's a lot of reasons to believe that it's actually quite difficult to outgas water. Okay, water wants to stay in the melt. And even towards the end of crystallization, water still has many ways in which it can remain trapped in the mantle. Okay? So we should think about these large steam atmospheres as being extreme end members, where we essentially are providing all the ideal conditions for water to outgas. Okay? When in practice, there are many physical and chemical mechanisms that would prevent that. Okay, so this is the key takeaway from this section. So magma ocean atmospheres are initially carbon-rich, okay, usually carbon monoxide. So if we're thinking about planet formation and evolution, we should be starting with a CO-rich atmosphere, okay, and then moving from that position, not starting with a steam atmosphere. They may never transition to water-rich. A lot of things have to go your way in order for the atmosphere to actually become dominant with H2O and effectively steam. And this is work that we've been sort of demonstrating over the last few years. Okay, so the final part, I would just like to talk about a new model that we're developing to probe these different interactions between mantles and atmospheres. And at the beginning, I showed examples from exoplanetary science, but I also spoke about solar system planets. And the idea, of course, is that the fundamental physics and chemistry should be the same, okay, for both of these. So rather than having models and frameworks that are good for terrestrial planets or solar system planets versus exoplanets, let's try and have a sort of a more holistic physical and chemical model that works for both. So this is what we've been working on now. And this has all been encapsulated into a new code that is called AppModeler. And the idea is, again, I showed that we have solubility measurements going back to 1964, okay? And at the moment in the exoplanetary literature, these are usually not known about or not accessed, simply because, of course, the publishing culture and the journals where people published have not yet sort of crossed over between exoplanet and Earth science. So what we're trying to do is basically encapsulate all of this knowledge we have from geoscience into a toolkit that planetary scientists, exoplanetary scientists can use to explore volatile exchange between mantles and atmospheres. So there's a few sort of different aspects that we include. In particular, It's quite common in exoplanetary systems to want to prescribe a range of different constraints. So sometimes we want to prescribe the amount of mass in the system, so the amount of elements by moles or mass. But sometimes we also want to prescribe pressures, okay? And so the idea is that this toolkit will allow you to prescribe different constraints depending on what you are interested in. Of course, we have a lot of solubility laws that we've incorporated. I'll talk very briefly about non-ideality, but the idea here is that when you get to high pressure, you do not behave like an ideal gas anymore, okay? You have to have a modified equation of state. And again, for complete accessibility across fields, there are many output options. Okay, so this is the basic scenario that we are considering. And the code at Modeler basically sits at this interface. So what it does is it tells you what the equilibrium chemistry is between your melt reservoir and your atmospheric speciation. Okay, so this will again provide a way of directly connecting planet formation models to observations. Importantly, as part of this this package, we've developed and implemented a lot of sort of standard software development processes that are used in industry, again to try and drive academia to sort of have the same sort of robustness when it comes to testing their codes and ensuring that they benchmark against existing software. So we have full logging, documentation, tutorials, and 100 tests to make sure that everything works as intended. Okay. It's also been designed to allow the construction of a model hierarchy. So what we didn't want to do is have a model where you would have to throw in a lot of complexity in order to generate output, okay? So the code will allow you to simply put in some amount of H2O or some amount of hydrogen, and you can just look at how it partitions between a melt and the atmosphere, okay? And then if you want to add in carbon species or you want to add in non-ideality or more complicated thermodynamics, you can do all of that, okay? So it's highly modular in terms of the way that it's structured. So as I mentioned, part of the package is a library of solubility laws. So we've been compiling solubility laws for different species. We've also been compiling equations of state for real gases. Of course, in the astrophysics community, there's in general a lot of knowledge about H2. So for example, the H2 fugacity coefficients have been of interest to this community for a long time. But in the geoscience, we also have information about how the behavior of, for example, CH4, okay, it depends on high pressure. And so we're trying to now bring all of this together into this work and this package and toolkit. So just to give you a few examples of the kind of things we can do, we can run sort of Monte Carlo experiments, so we can run tens of thousands of different atmospheric scenarios, and then we can look at the output. So these here are corner plots, but importantly, this is the amount of H2O in the atmosphere at 2000 Kelvin, and this is 2.5%, and you can see for all the cases, it's basically less than 1%, okay? So this again is adhering to what I mentioned earlier, that the water very much likes to remain in the mantle. You can also see that you essentially have a sliding scale between CO2, carbon dioxide, and carbon monoxide, depending on this FO2 parameter, okay? So this is why I mentioned earlier, the earliest atmospheres are carbon-rich, okay? You're either CO2 or CO-rich. Okay, so if we go back to the solar system atmosphere question about Venus and Mars having a CO2 over N2 and Earth being different, we can begin to address this question. And what we do is that we can take the initial atmosphere that was in equilibrium with the magma ocean for Earth, and then we put that atmosphere in a box and we just cool it, okay, to the present day equilibrium temperature of Earth. And what if we do that, so this is the magma ocean atmosphere and this is the cooled atmosphere, what we find is that we end up with around 80 bar of CO2 and 2 bars or so of N2, okay, which again, we'll give you a CO2 over N2 ratio of about 35, okay? So what this sort of implies is that actually the early atmosphere of Earth was probably comparable to Venus, okay, that we see today, okay? Which makes sense, because they would have evolved from a magma ocean, they would have equilibrated, and then the atmosphere would have cooled. Of course, the reason then that Earth is different is probably because we have cycling between the interior and the atmosphere at present day, driven by carbon silicate cycling, for example. So plate tectonics, again, is probably the long-term geological modifier that has effectively drawn out carbon from our atmosphere, and it hasn't operated, or at least not operated on average long enough on Venus to impact the atmosphere. Okay, so I'll wrap up here with a couple of lessons that I would like you to sort of take away from this talk. Okay, so first of all, sort of interpret H2O atmospheres cautiously when you read about them. Okay, they are extreme end members. They assume a lot of catastrophic outgassing and often do not consider the effect of solubilities. And therefore, when you do this, CO-rich atmospheres are actually the most common statistically to have for terrestrial planets. Rocky planets have multiple mechanisms to retain their water during magma ocean epochs. And indeed, I think it's interesting, one of the features of water, of course, water is special in so many ways, but another one of the features in which makes it special could be its high solubility, okay? And so during this sort of tumultuous time of planet formation and impacts, for example, the water could have actually been quite, safely harbored inside the planet in this melt reservoir, and then obviously outgassed later to some extent in order to provide surface liquid water. So I think the solubility of water is another interesting chemical property that could be quite important. As I also showed, when interpreting observations, what you see in the atmosphere is not necessarily representative of what is in the interior or the bulk composition, okay? And so in exoplanetary sciences, what we're currently seeing is that people are wanting to draw one-to-one correlations between, I see, a volatile-rich atmosphere, and therefore the whole planet is volatile-rich, okay? Or therefore the bulk composition is rich. But we should take into account the fact that these different species have different solubilities, and therefore we can't draw a one-to-one correlation. We have to account for the solubilities. And so therefore, observe low abundances in an atmosphere do not mean necessarily that the planet doesn't have volatiles. In fact, the planet could have lots of volatiles. They're all just inside the planet, okay? And then third lesson, C over H is equal to 1 for Earth, okay? So again, as sort of planetary scientists are coming down, thinking from gas giants, they're usually preoccupied with hydrogen and helium, okay? But as you move down towards sub-Neptunes and super-Earths, don't forget about carbon and oxygen, okay? And therefore, for meaningful results, I sort of recommend considering, these 6 species here so that your models are accounting for all the diversity that could be relevant. Okay, so here are my takeaways. So early CO-rich atmospheres are common, not steam. Volatile pore atmospheres do not mean the interior or the bulk is volatile pore. Don't forget about carbon and oxygen if you're modeling atmospheres. At least say, implicitly what your assumptions are. And we've encapsulated a lot of this into a new code app modeler, but we're continuing to develop the GitHub for the web, for the group. And this will have a lot of other codes to help you with geochemistry and thermochemical modeling of atmospheres moving forward. Okay, thank you.
Thanks, Dan, for a really comprehensive talk on rocky planets. Time for questions. Alex.
Hey, great talk.
Thank you.
I was wondering, so as you say, your code sits at this interface between the the main bulk interior of the planet and the atmosphere. So about those one-to-one conclusions that people want to draw, could you use this kind of code to provide some sort of probabilistic sample? So if we see this in the atmosphere, for which species is it, say, at a certain probability that, just based on the amount of time that you would expect with a given composition, that you could draw it? Because that would seem quite useful, right? Then you could say which species you can actually use to make these inferences and which you can't. Is that something that this code can achieve and is of interest?
Absolutely, yeah. So this can achieve part of that, of course. So there are, and I've not spoke about it, but because we're dealing with the interface, of course, you have the rest of the atmosphere as well, okay, which has a PT structure, pressure temperature structure, which will also have different chemistry. It could be non-equilibrium chemistry. And of course, you also have photochemistry and escape processes that are happening at the top. There are codes out there that people are working on and that we can effectively couple to sort of do an upward continuation. of our interface chemistry through the atmosphere to then do a direct comparison with observations. So this is just one tool that will hopefully help with that. But absolutely, the point being that there are increasingly awareness that the observation deck is usually a fraction of a bar, a few millibars, and this is not the pressure at which the gas is in equilibrium potentially with a magma ocean, and we need to be able to sort of draw a line between the two and be able to track composition, speciation.
Yeah, that was going to be my next question, actually, because, yeah, as you say, you can do it quickly, but you've completely removed pressure from the equation for your experiments, but I gather you can still draw inferences in these high-pressure environments anyway, somehow?
Yeah, so remember that ultimately the pressure effect is incorporated in the equation of state, which are the non-ideal equations of state. So essentially, this is telling you how much the behavior of a gas departs away from ideal. So usually, for up to 1,000 bar or so, you're okay with assuming ideal behavior, but then you become non-ideal. And so there are geochemical experiments at high pressures where you can infer these fugacity coefficients. It gets more complicated because, of course, gas mixtures also behave non-ideally, so they don't necessarily behave in an ideal fashion. That also has to be taken account of.
Okay, thanks.
Yeah.
Any other questions?
Perhaps a very naive question by an amateur. So a few slides back, where you showed like the evolution of Earth. Yeah, this one. So CO2 over nitrogen ratio.
Yep.
So you said that this is in your evolution that would be the present day ratio on Earth, right? Very similar to Venus. So I was wondering, how would it continue evolving if you were just run your evolution for another billion years or whatever?
Yeah, exactly. So this model is only considering the initial collapse of this hot atmosphere. So you start out for Earth conditions at this point here. So you have, again, some CO2, and again, you're dominated by CO. And then you imagine putting your atmosphere in a box and just rapidly cooling the atmosphere down to the equilibrium temperature also. And so what this is showing, of course, is that you begin to precipitate graphite, okay, and then, of course, you eventually produce liquid water. And at the end of that state, you end up with an atmosphere that is like Venus at present day. But again, this is only soon after the magma ocean stage. So this is only going to be maybe up to 100 million years, probably less, after the Earth was fully accreted. And then you have 4.4 billion years plus of geological time where you can then process the CO2 and N2. And so assuming that, and this is not a given because we don't know when plate tectonics started and there's a lot of debate in the community, but if you assumed that you had an efficient mechanism to then draw down carbon back into the interior, then you can begin to draw down CO2 relative to N2, and then you can drive, again, presumably based on this, the CO2 level down by 4 or 5 orders of magnitude in a few billion years, which, again, seems quite efficient, but you have the carbon silicate cycle for which there's a lot of data and information on, and this will give you, an estimate of the drawdown timescales. And so, so it's a longer-term geological evolution that effectively modifies this to the 10 to the negative 4 value that we have at present day.
Okay, yeah, Sophia.
As a follow-up question, to what extent is the reduction of CO2 modified by the presence of life on Earth?
Yes, it is. So of course, again, this is pushing beyond the magma ocean stage clearly, and so, but very clearly, life indeed modifies the planetary surface and the planetary atmosphere, and so this is going to be one of the challenges moving forward, of course, with exoplanets, when people are thinking about what is the chance we could detect some level of life. There's also interesting ancillary questions such as, the conditions to get life started may not be the same as the conditions to maintain life, okay? So if, for example, we find planetary atmospheres and we infer that this could maintain life, it doesn't mean that that was the condition that actually got life started, okay? And again, for the early Earth, we know the conditions were very different, and that may have got life started, and then subsequently the planet and life have evolved in sync and sort of become this sort of symbiotic system and has kept things sustained. So it's definitely a very complicated question, and that's to some extent why the simplest thing to do is to start with, these early atmospheres where you don't have any life, and then you look at planets and you say, well, how does the planet's atmosphere compare to our predictions from the earliest primary atmosphere? How much has it been modified? And so then you're looking for sort of a delta in the atmosphere. And you would assume that if we find atmospheres like this that agree with the models, then it remains a relatively primary, primitive atmosphere. But substantial modification could involve life at various points during the planet evolution, maybe not even when we're observing it, but previously. So it's a good question. And it's hard to know how we will deal with that. Other than statistically, of course, we will just have to have a probabilistic answer to those types of questions.
Thank you.
Okay, I think probably talking about life and lunch time, perhaps it's good time to stop. So let's thank Dan again. So Dan is also around all afternoon, so if anyone would like to set up meetings with him, so just feel free to talk to him. He is in the office next to the coffee room. Thank you.
Thank you.
And this also marks the end of the seminar season, right? So we will reconvene sometime in September. You will hear from us. Thank you for being with us all this time.